All right, let's dive in. Today we're talking about one of the most powerful and kind of secret ideas in all of chemistry, chemical equilibrium. It's the invisible engine that's running pretty much everything around us, from what keeps your soda fizzy to how your body even uses oxygen. It's everywhere.
So you've probably been taught to think of chemical reactions as a one-way street, right? You mix some reactants, they turn into products, and boom, reaction's over. But what if that's not the whole story? What if it's less of a one-way street and more of a busy two-way highway? Do these reactions ever actually stop?
Well, that question gets us right to the heart of it. For most reactions, there's no finish line, they just sprint across. Instead, they reach this incredible balancing act. Imagine that two-way highway. You've got reactants becoming products, and at the very same time, products are turning right back into reactants.
And the key word here is dynamic. You see, static equilibrium is, well, it's boring. It's a book sitting on a table. Nothing is happening. But dynamic equilibrium, it's like a really popular store. The number of people inside might look constant, but that's only because people are coming in at the exact same rate that other people are leaving. From the outside, it looks still, but inside, it is buzzing with perfectly balanced activity. That's our chemical reaction.
Okay, so if reactions are doing this constant back and forth dance, how do we describe that state of balance? Well, it turns out every single reaction has a unique fingerprint that tells us exactly what its equilibrium looks like. So let's open up our chemist toolkit and grab our first tool. It's called the equilibrium constant, and we just call it K.
Now, K sounds kind of formal, but the idea behind it is surprisingly simple. It's just a ratio. It compares the amount of products to the amount of reactants once everything is settled down. And what's so cool about K is that for any reaction at a certain temperature, it will always find its way to this exact same ratio. It's like the reaction's destiny.
And we calculate it with this simple fraction. You put the concentration of your products on top and the concentration of your reactants on the bottom. The only little trick is that you have to raise each one to the power of its coefficient. You know, that big number out front in the balanced equation. Do that and you get one single, super powerful number that tells you the whole story.
And this one number tells us so much. If K is a really big number, way bigger than 1, it means the top of our fraction, the products, is huge. The reaction just loves making products. We say the equilibrium lies to the right. But if K is a tiny little number, like a decimal, then the bottom of the fraction is bigger. The reaction is perfectly happy staying as reactants.
Okay, knowing the final destination K is awesome. But what if you're in the middle of the reaction? How do you know which way it needs to go to get to that equilibrium? For that, we need our second tool from the toolkit, the reaction quotient, or Q.
And here is the really clever part. You calculate Q with the exact same formula as K, products over reactants. The only difference, and this is the whole point, is that you can plug in the concentrations from any moment in time, not just at the end, but right in the middle of the action.
The absolute best way to think about this is with a GPS analogy. K is the final destination you typed into your map. Q is that little blinking blue dot that shows you where you are right now. And by comparing those two, you know exactly which way you need to turn.
And the roadmap is super simple. If your current spot, Q, is smaller than your destination, K, it means you don't have enough products yet, so the reaction shifts to the right to make more. If Q is bigger than K, whoops, you've overshot it. The reaction has to shift back to the left. And if Q equals K, perfect, you've arrived. The system is at equilibrium.
All right, now for the part that I think is the most amazing. Knowing all this stuff isn't just about watching reactions, it's about controlling them. This is where we stop being spectators and we actually get into the driver's seat.
This is Lee Chatelier's principle, and it is the golden rule. Basically, it says that a system in balance is happy and it does not like to be disturbed. So if you mess with it, if you apply a stress, like changing the temperature or adding more stuff, the system is going to push back. It's going to shift to try and undo what you just did.
And these stresses are our control levers. So if you add more reactants, the system says, whoa, too many reactants, and it shifts right to use them up. If you crank up the pressure on some gases, it'll shift to whichever side has fewer gas molecules to relieve that pressure. But temperature is the real game changer. It's the only stress that can actually change the value of K itself. It literally changes the reaction's destination.
So far, we've really been talking about the big ideas, the conceptual why. Now, it's time to get into the nitty-gritty, the how.
These are the actual mathematical tools chemists use to get this stuff done with real precision.
There are just a few rules of the road to remember. First, pure solids and liquids, you just leave them out of the expression. Their concentrations don't really change, so we ignore them. Second, if you flip a reaction around, the new K is just 1 over the old K. And finally, if you multiply an entire equation by some number, you just raise the original K to the power of that number. Easy enough.
Now, for reactions with gases, we sometimes find it easier to work with pressure instead of concentration. This gives us a slightly different constant called Kp. But don't worry, it's super easy to convert between the two with this formula here. That little delta N, is just the change in the total moles of gas from reactants to products.
And now, for the absolute workhorse of equilibrium math, the ICE table. I stands for initial, change, and equilibrium. It's just a simple way to keep our numbers straight. We start with the I row, and all you do here is write down what you started with, the initial concentrations of everything in your beaker.
Next up is the C row for change. As the reaction chugs along towards equilibrium, you're going to lose some reactants and gain some products. We don't know exactly how much yet, so we just call that amount X. We use a little bit of algebra to represent the change.
And finally, the E row, equilibrium. You just add the initial and change rows together. This gives you these nice little expressions for your final concentrations, all in terms of X. Now you can plug those into your K expression and solve for X. This is the tool that connects all the theory to a real hard number.
And you might be thinking, okay, that's a lot of theory, but this is not just an academic exercise. This entire toolkit gets used every single day to solve massive, real-world problems. The classic example is the Haber-Bosch process. By using Le Chatelier's principle, high pressure, just the right temperature, chemists can force this reaction to make huge amounts of ammonia, the key ingredient in fertilizer.
And the impact of this one process? It is absolutely staggering. This single reaction, which was mastered using the exact principles we just talked about, is responsible for the nitrogen in the food that feeds over half of the entire human population. That's the power of controlling equilibrium.
So just think about the journey we just took. We went from just watching reactions happen to being able to predict their destination with K, track their progress with Q, take the wheel using Le Chatelier's principle, and calculate the exact outcome with icy tables. You're not a spectator anymore. You're in the driver's seat.
This knowledge is incredibly powerful. So I'll just leave you with this final thought. Now that you have the toolkit, now that you know how to understand, predict, and even control chemical reactions, what global challenge are you going to solve?